Hello everyone. Today we are going to make an experiment about the features of period in simple harmonic motion. We are going to testify angle from the center, effective gravitation with an incline, and length of the string to see how they affect the period in simple harmonic motion. Here, you can see the equipments that I'm using for this experiment. We have a string that glued to a puck. We are using the system to see simple harmonic motion. We are using an air table as a surface to prevent energy loss due to friction, and also a stopwatch is used to calculate period. Then, there is a ruler and a protractor to calculate what angle and length we set free our puck. There is a block to provide incline to the surface. Last but not least, there is also pencils and a paper to calculate the period from the signs that left by the puck on the paper. There is also additional timer to have a definite assurance about the period. To break down the physics behind our experiment, we explore the motion of a pendulum, which is an example of simple harmonic motion. When a displacement angle is small, the motion of a pendulum is governed by forces, primarily gravity, and can be described using the concept of periodic motion. The period of a pendulum is the time it takes to complete one full oscillation, and it's influenced by several factors. One of them is the length of the string. The longer the string, the greater the period because the pendulum has a larger arc to travel, and this relationship is governed by the formula T equals 2 pi times the square root of the length of the string divided by the product of gravitational acceleration and the sine of the inclined angle. Secondly, the gravitational acceleration is also one factor. The force of gravity determines how quickly the pendulum moves back toward its equilibrium position. By adjusting the incline of the surface, we change the effective gravitational acceleration. The term G product of sin incline angle accounts for the gravitational force acting along the incline. Incline of the surface is also one of the factors. In our experiment, the incline angle played a key role. For the control setup, we set sin incline angle to 0.1, and for the variable incline, we set that to 0.14. This change effectively increased the component of gravitational acceleration acting on the pendulum, which reduced the period. And last, but not least, the release angle was also used as a variable in our experiment. When the pendulum is released, the angle from the center impacts the initial potential energy. However, for small angles, typically less than 15 degrees, the motion closely approximates simple harmonic motion, meaning the period is independent of amplitude. This is known as the small angle approximation. The period motion of pendulum is an excellent demonstration of the conservation of energy. At its highest point, all energy is stored as gravitational potential energy. As the pendulum swings, the potential energy converts into kinetic energy at the lowest point, where the pendulum's speed is greatest. Real-world factors such as air resistance, friction at the pivot point, and timing errors can cause deviations from the theoretical predictions. Despite this, the experiment showcases the dependence of the period on measurable variables like string length, gravitational acceleration, and release angle. By understanding the relation between these factors, we can deepen our grasp of the mechanics of auxiliary systems and their application in various fields, from clocks to engineering dynamics. First of all, we glue our string to the puck, and then we calculate the length of the string with a ruler, and then we sign this length with a pencil. Secondly, we use a block to give an incline to the surface. For example, in our control setup, the incline angle sinus equals to 0.1. Then, we use a protractor to calculate the angle from the center. Now here's an example of how the setup works. As you can see, There are dots left by the puck on the paper. We calculate the number of dots to get the half of the period, since it only left sign in one oscillation. There is also a timer to be sure about our calculations. Now, we change our features to get different periods. For example, in the variable incline setup, we change our incline from 0.1 to 0.14. Here, you can see the data that I obtained from the experiment. Now, let's talk about the results, the errors, and how we can interpret these findings. In this experiment, we observed the period of a pendulum under different conditions, such as varying string length, incline, and angle from the center. Now, let's talk about these key findings. First of all, I want to begin with the control setup. In the control setup, where all variables were kept constant, we measured the period to be 3 seconds. This was compared to the expected value, which was 3.5 seconds. The difference between the measured and expected values suggests that there might have been a small issue in the experimental setup or the measurement techniques. One possible cause for this difference could be accuracy of timing or the friction between the string and the puck, which wasn't accounted for. This would lead to a slightly shorter period than expected. Now, for the variable length setup. In the variable length setup, we use the string length of 20 centimeters compared to the control setup's 30 centimeters length. The measured period for the shorter string was 3.4 seconds, while the expected value was 2.8 seconds. The difference could be attributed to a few factors. One possible explanation is that the string length affects the moment of inertia, and perhaps there was an external force or measurement error that affected the timing. Additionally, the shorter the string may have led to faster oscillation, but we saw a longer period than expected, which could also be related to measurement inaccuracies, as I mentioned in the control setup. For the variable incline setup, in this setup we had a variable incline where we increase the effective gravitational acceleration by changing the incline angle. The measured period was 4 seconds, while the expected period was 2.9 seconds. This substantial difference suggests that the incline's effect wasn't fully accounted for in the calculations. The acceleration due to gravity is altered on an inclined surface, and if the angle or the actual effective gravitational acceleration wasn't measured precisely, this could explain the discrepancy. Additionally, errors in timing, as I mentioned in the control setup, such as using a spark timer with slight inaccuracies, could contribute to the difference. And lastly, for the variable angle setup, in the setup where we changed the angle from the center, the measured period was 3.4 seconds compared to the expected value of 3.5 seconds. This result may relatively close to the expected value, which suggests that the angle, as long as it was kept within a small range, didn't contribute much error. It shows that in the small angles, our result is going to be more accurate to the formula. However, it is important to note that even slight variations in the angle could have had small effects on the period. In this case, the measurements appear to be accurate, but small discrepancies could still arise due to factors like precision of the angle measurement or slight timing errors. To summarize, the discrepancies between the expected and measured periods in some setups can be attributed to several factors, such as timing errors. For example, maybe there was an issue with the timer, or the signs left was not the accurate number. Or inaccurate angle or string length measurements also may affect that result. And the effects of friction or air resistance there were not accounted for. Despite these errors, the general trends observed in the data were in line with the theoretical expectations, such as the period increasing with the string length and decreasing with the incline angle. For future experiments, improving the accuracy of timing, reducing friction, and more carefully measuring the angle and length could help reduce errors. Overall, This experiment demonstrates the complex interaction between variables in simple harmonic motion and provides a good basis for further investigation into effects of different parameters on pendulum motion. I want to thank you for watching this video and give your time to this experiment.